Okay, here we are with some exercises. I've got 4 exercises picked out for section 1.8 to go over the ideas that we just learned about one-sided limits, two-sided limits, and some of the properties of limits. So first off, this is number 1 in the textbook. And just like some of the questions we saw from section 1.7, it gives us a graph and asks us to find the limit of the graph, the limit of the function at various points. So let's start in. I think we'll just do a couple of these, maybe not all of them. The first one, part A, asks us to find the limit of f of x as x approaches. Now this could be a little tricky because we have a negative sign and a plus sign. This is x approaching -1 from the right. So let me write that. That's x approaching, maybe the parentheses will help, -1, but from the right. So we go to our function here. We look at our x value of -1. Right, here's our origin. Here's 0, 0. So here's -1. And we say, what does it look like the function should be if we ignore the actual value at -1, but we look at the x values that are just to the right of it, because we've got this plus, we're looking to the right. So just to the right, the function is here. And what does it look like the function should be? Well, it looks like it should be 1. Now in this case, the function is actually 1 there, but that's irrelevant for the limit. It just happens that right here, the function is continuous. And if you remember, if a function is continuous, the limit there is just the value of the function. So A just looks like it's 1. Now let's look at B. B is approaching 0 from the left. So we look at 0. We don't care what actually happens at 0. So we don't care that it actually jumps up to there. That's irrelevant for finding the limit. But we look at the x values just to the left. Just to the left, the function is right here. And it looks like as it approaches 0 from the left, the value should be 0. So even though the value is actually 2, we don't care about that. From the left, it looks like it's going to be 0. Okay, let's do just one more. Let me take a look. Let's do D. And then I'll leave the other 3 parts for you to look at on your own. So in D, we're approaching 1 from the left. So here's the x value 1. We look at the x values just to the left. And then we look at the function at those x values. So at the x values just to the left of the 1, here's our function. And it looks like f of 1 should be 1. Now, it doesn't matter that f of 1 is actually 3. That's irrelevant. It's just when you look from the left, it looks like it's going to be 1. If you look from the right, that's a different question. Then it looks like it's going to be 2. So from the left, it looks like it's going to be 1. From the right, it looks like it's going to be 2. And that might help you answer part E, which I'll let you do on your own. Moving on to our second question. This is number 7 in the book. It gives us some information and asks us to use that information to compute a different limit. So this is all about using those properties of limits. In the actual question that I've picked, only G appears. So for this question, the information about F and the information about H are extraneous. We've got this limit here. Now, the way that they have this squared here, I think is really confusing. So let me tell you what they mean. They mean the limit as x approaches to of g of x squared. And I guess you could put extra parentheses if you want. But the point is that the squared is inside of the limit, not outside. I'm fairly certain that that's what they mean. Otherwise, it would be a kind of silly question. So one of our properties of limits, by property, okay, I'm just guessing here, but I think it was property 3. That told us, let me remind you, that the limit as x approaches some number c of f times g, so the product of any 2 functions, is equal to the limit as x approaches c of f times the limit as x approaches c of g. So if I have a limit of a product, and I know the individual limits, I can split it apart like this. Now, this required knowing ahead of time that these 2 limits exist and are finite. Otherwise, it's not valid. So what we know is that the limit as x approaches 2 of g exists, and it's finite. It's -4. So we can apply this property to g of x squared. Now the tricky thing is that g of x squared is really just g of x times g of x. So this equals, the limit as x approaches 2, of g of x times g of x. Maybe it's a little bit easier to see what we're about to do if we write it out like that. And now by the property, that's the limit as x approaches 2 of g of x times the same thing again. The property says that we can take the product and split it into 2. We know what this limit is. It tells us it's negative 4. So this is negative 4 times negative 4, which is 16. Now hopefully before I just did that problem, you paused and you tried it yourself. If not, let's make sure that we do this on this next problem. So here it is. I would like you to first pause, try to figure it on your own. In fact, you might be able to do this one just in your head. You might not even need to write anything down. But it's important that you're taking an active role in this learning process. If you just take a passive role by watching me, you'll never be able to do it on your own when it comes time for quizzes and exams and whatever. So this question says, find the limits using your understanding of the end behavior of the function. That just means you should know what the function looks like, and so you should know the answer is basically what they're saying here. So this is asking for the limit as x goes to infinity of x cubed. Let's start by drawing x cubed. We don't need a very precise graph because we're interested only in that end behavior, but it looks vaguely like this. And we talked about this a lot in section 1.6 when we talked about powers and polynomials. And as x goes to infinity, the value of x cubed goes off to positive infinity. So once you know what the graph looks like, you know the answer. It's just infinity. Now sometimes you'll see the book write positive infinity. That means the exact same thing. That's just to emphasize the positive one instead of the negative. But if you just write infinity, that implicitly means positive infinity. Okay, this is going by quickly. We've just got one more problem. We've saved the hardest one for last, although I promise it's not too hard. The question is to evaluate the limit as x goes to infinity of this function. So we're looking for the end behavior. This is not a polynomial, but it's one of those rational functions that we also saw in section 1.6. It's the fraction of two polynomials. So I'll show you two different ways to solve this. One is kind of like when we were doing the 1.6 problems, and the second one is one that you'll see the book use sometimes, and you can use whichever one you like, but I'd like you to see the two different ways to do it. So first let's think about what happens when we plug in a very big number. Very big positive number. What happens when we plug in a very big positive number? Well, the numerator is that very big positive number minus 5. Okay, so if this is something really, really big, then subtracting 5 doesn't really change it that much. The denominator is 5 plus, 5 is not going to matter when you're talking about really big numbers, 2 times x squared. So what you want to realize here is that the x squared, that's the biggest power of x. And so when you're looking at really big x values, the x squared is going to be way bigger than the x to the 1. So this numerator is going to be some big number, a positive big number, but this denominator is going to be a much, much, much bigger positive number because it's growing quadratically instead of linearly. That means a second power versus a first power. And so what happens is that f of x approaches 0. Or to write it a little bit more concretely, the limit as x approaches infinity of f of x is 0. Now, a lot of times you learn this in a pre-calculus class. You've got a couple different situations. Situation 1 is if the degree of the numerator, remember the degree is the biggest power, if the degree of the denominator is bigger than the degree of the numerator, then the limit is 0 as you go to infinity. If they are equal, you might have learned, then you look, so if you had a second degree term here, let's pretend we had a plus 5x squared. If the degrees are equal, then you look at the ratio of their coefficients. So here it would be 5/2. And if the top is bigger, so if you had a 5x cubed, then those rules don't apply and things can get more complicated. So you might have learned that in pre-calc. Now, one other way that you'll see the book do it, so I want to show it this way as well. The book likes to divide the numerator and denominator by the largest power of x. I'll show you what I mean. So the largest power of x here is 2x squared. So we can take our, the largest power is just the 2 because of the x squared. So we can take our fraction, and let's multiply the top and the denominator by 1 over x squared. You're allowed to do that to a fraction. As long as you multiply the top and the bottom by the same thing, you haven't changed the fraction. So what we get in the top, we get x times 1 over x squared. That's a 1 over x minus 5 over x squared. What we get in the denominator is a 5 over x squared plus 2. Okay, so now the key is that as we go to infinity, anything with an x in the denominator has to go to 0. 1 over x definitely goes to 0. That's 1 over a bigger and bigger number. 5 over x squared, that goes to 0 even faster. So it doesn't matter that this is a minus sign because you're minusing 0. So as x goes to infinity, this goes to 0, this goes to 0, this goes to 0, and of course 2 just stays 2. So by dividing by the biggest power of x, you're certain that you've got a constant somewhere, the 2, and everything else goes to 0. So that's just going to go to 0 over 2, which is 0. Both of these are totally fine ways to think about this. This is the way that we thought about it mostly in section 1.6, and this is the way that the book also describes it. So that's it. Those are the 4 problems. This was a fairly quick video, only about 12 minutes. I hope this has helped out, and I look forward to seeing you again in section 1.9 when we'll look at limits just a little bit more.